We're going to do a couple more problems that involve solving nonlinear systems. In exercise 5, we're solving the system y equals 5x, y equals 1 over x. Now, you might think, why is this a nonlinear system? Because it looks like we just have x to the first power in both of these. But when we have x in the denominator, the equation is not linear. In fact, the graph of y equals 1 over x we looked at quite a bit earlier in this course. It's a rational function graph with two branches. The x and y axes are asymptotes. And it's actually a hyperbola. We didn't call it that back then. But there's the graph of y equals 1 over x. It's a curve with two branches, not linear. Y equals 5x. The other equation has a graph that's a straight line with y-intercept through the origin and slope 5. So I'm just drawing a rough sketch here. And it looks like we're going to have 2 points of intersection is my guess. You don't have to do this analysis ahead of time, but that's I think you should be able to have that kind of picture in your mind before you start this problem. So now notice that we have y isolated in both of these equations. So I can go right ahead and make a substitution to solve. So I'm going to actually take the second equation, y equals 1 over x, and I'm going to replace that y with 5x from the first equation, right? So I get 5x equals 1 over x, and I got to solve for x now. To solve for x, I want to clear denominators from this equation. So I'm going to multiply both sides by x. And so the left-hand side becomes 5x squared, 5 times x times x. The right-hand side, the x's cancel, and I'm left with just 1. And now, before I can solve for x, because I have an x squared here, I want to isolate x squared. Always isolate the variable squared before you take square roots. So I'll divide both sides by 5. And I get x squared is equal to 1/5. I'm going to move up over here to the side. Now I want to take square roots. So x is equal to plus or minus the square root of 1/5. And I can take that apart into the square root of the numerator, which is 1 over square root of 5 in the denominator. And in many instances, you can just leave the x coordinates in that form. But if you want to rationalize the denominator, get the square root out of the denominator, you can take that and multiply by square root of 5 over square root of 5. And then we get x equals, because we're multiplying by 1, so we're going to change the look without changing the value. We end up with plus or minus 1 times square root of 5, which is square root of 5, over square root of 5 times square root of 5 is 5 outside the square root sign. So we have our two x values now. So x is equal to square root of 5 over 5, or x is equal to negative square root of 5 over 5. And I have to find the corresponding y values. And so what I'm going to do is go back to one of my original equations. I guess y equals 5x is the easiest one to use. And I'm going to substitute in my x values. So I'm taking y times square root of 5 over 5. That 5 times is just like 5 over 1. So the 5's will cancel, and I get y is square root of 5. So my solution is square root of 5 over 5, comma, square root of 5. And I have another solution here, so I have to plug my other x value into y equals 5x. So that's like y equals 5 over 1 times negative square root of 5 over 5. Now again, the 5 will cancel, and positive times negative is negative. I get a negative result. Negative square root of 5 over 1 is just negative square root of 5. And here's my other solution. So my x was negative square root of 5 over 5, and my y is negative square root of 5. So it's just the negatives of the coordinates I got from my first solution. And there we go. 2 solutions for this problem. Let's see if I can back out a little bit. Here's that whole problem on one screen. And we're going to do one more example of something a little bit different. I wanted to do at least one example where we don't use a standard substitution. We don't use that addition method that we talked about in the one problem where we had just x squareds and y squareds. I'm going to use a substitution, but what I want you to notice here in this number 6, so x squared minus 2y squared is 4. 3x squared minus y equals 14. X squared occurs in both equations. And there's no x term, x to the first power term in either one. So I'm going to do something called sort of a special substitution. I wouldn't memorize this. I just think I want you to see that this type of thing could be performed. Or what I'm going to do is I'm going to isolate x squared in equation 1. I guess I should go ahead and number these 1, 2. And so take that first equation, and I'm going to add 2y squared to both sides. So x squared equals 4 plus 2y squared. And then I'm going to substitute the x squared into equation 2. So I'm going to take equation 2, the second one, 3x squared minus y equals 14. And I'm going to use this idea for the substitution that we got by isolating x squared in equation 1 and replace x squared with that 4 plus 2y squared. So I have 3 times 4 plus 2y squared in parentheses minus y equals 14. And now I have an equation that I can solve for y. I have to distribute 12 plus 6y squared minus y equals 14. Looks like I have a quadratic equation in y. So 6y squared minus y plus 12 equals 14. I want to subtract 14 from both sides so that I get one side equal to 0. 6y squared minus y, that'll be minus 2 equals 0. And this is a messier looking, crazier looking quadratic equation I have to try to solve. Quadratic formula is fine. I'm going to try factoring. See if that works first though. 6y squared, now that's a challenge because it could be 6y and y and 6y. It could be 3y and 2y, 2y and 3y. But now I know my sign's got to be different because I have a negative third term. And 2 is either 2 and 1 or 1 and 2. If I put 2 and 1 here, I want a negative sign in the middle. So I want inside, I want a negative 4y plus outside positive 3y will give me that negative y. So this is a factorization that will work. 3y minus 2, 2y plus 1. 3y minus 2 equals 0, or 2y plus 1 equals 0. So y is equal to 2/3, or y is equal to negative 1/2. Now I still need to find the corresponding x values. And so, let's see, I have to pick something to plug into. I guess I don't see reason to prefer one equation or the other here. I'm going to take 3x squared minus y equals 14. I don't think it matters at all. I'm going to substitute in the y. And I have 3x squared minus 2/3 equals 14 when I substitute in here. Okay. And now I could add 2/3. I can first, there are different ways I could proceed here. I'm going to multiply both sides of this equation by 3. I got to distribute the 3 through the parentheses on the left. So I get 9x squared minus 3 times 2/3. I'm writing that out because the 3 is going to cancel, equals 3 times 14 is 42. I have 9x squared minus 2 equals 42. So 9x squared is equal to 44. Isolate x squared. X squared is 44 over 9. Now take square roots. So it's getting a little hairy, but so x is plus or minus the square root of 44 over 9. I can write that as plus or minus, that's the square root of 4 times 11 over 3. X equals plus or minus 2 square root 11 over 3. Whoa. There I got my x coordinates. That corresponded to, where did all that start out? Way up here. Y was equal to 2/3, right? So 2 square root 11 over 3 2/3 for y. Or negative 2 square root 11 over 3 2/3 for y. So we got two solutions there. And now I'm going to back up, draw my line here, and go do the same with the y equals negative 1/2 solution. So 3x squared minus y equals 14. 3x squared, now I'll get minus a negative 1/2 equals 14. That's 3x squared plus 1/2 is 14. And so to clear denominators here, I'm going to multiply both sides by 2. And I have to distribute on the left, of course, again. And what I get is 6x squared plus 2 times 1/2 equals 28, where the 2's cancel in that one fraction. So I have 6x squared plus 1 equals 28. And So 6x squared is equal to 27. Subtract 1. Now I have to divide both sides by 6. So x squared is 27 over 6. That means x squared is 9 over 2. I can divide by 3 above and below there. And now I'll take square roots. X is plus or minus the square root of 9 halves. So x is plus or minus 3 over the square root of 2. And I can multiply above and below by square root of 2. I need my plus or minus sign there. So x is equal to plus or minus 3 square root of 2 over 2. Whoops, let's keep it on the screen. And I have two more solutions now coming out of this. 3 square root of 2 over 2 for x, and the y value we're working from was negative 1/2. And I also have negative 3 square root of 2 over 2, negative 1/2. So for this problem, we got 4 solutions. Using this special kind of substitution is how we got started. Now if I go back to these original equations, the first equation has a difference of squares here, x squared minus 2y squared. That's a hyperbola graph. And the second equation has x squared, but y is not squared. So that second equation is actually a parabola, right? So we have a situation. I'm going to just sort of bring the work up here slowly and move both sheets. So I don't think I'm going to be able to fit this all on the screen at once. And what I just want you to realize here is, so we have this situation where we had a hyperbola. You can check to see the intercepts are on the x-axis. And then we have this parabola in the picture. And there are 1, 2, 3, 4 points of intersection. That's what we're finding. Again, you don't need the graph, but that's the graphical interpretation. So here are my solutions. I'm going to back it up one more time so that we can get the original problem on there. There's the original problem. And that got us to the 2y values. From the 2y values, y equals 2/3 and y equals negative 1/2. We had to go through that work to find the corresponding x's. And maybe I'm going to stop it there for a second. And then just slide it up one more time to the solution. So that's our last problem that we're doing together on nonlinear systems.